Hi everyone, welcome to part 5 of the video series on alkenes. In this one, we're going to be focusing on oxidation and reduction of alkenes and talking about the different ways that we can form carbon-oxygen bonds or reduce alkenes down to alkanes. All right, so first let's quickly just cover the difference between reduction and oxidation. So for the reduction of alkenes, we're looking for an increased number of CH bonds. And so that's similar to this first example here that we have here, where we go from having a alkene to an alkane. And that corresponds to an increased number in the hydrogens, because now we have two on each of those carbons instead of the one carbon hydrogen bond that we had before. In comparison to the oxidation is the increased number of CX bonds, where X is some more electronegative atom, and usually it's an oxygen in this chapter. And so that we can see in this middle one, where we can see that both of these CO bonds begin to be C double bond to an O. So we increase the number of bonds between carbon and oxygens. Same thing is true for this bottom bond here too. All right, if we take a look at this last one, we can see that before we had two bonds between a carbon and an oxygen highlighted in blue here. And in the end, we only have one here. And we actually increase the number of hydrogen carbon bonds that we have here by adding in another hydrogen to that left or right carbon. And so this would be a reduction here. And it's a little bit more tricky to see because it's not just like the standard carbon hydrogen or increased number of carbon oxygen bonds that we see with most reduction oxidations. But all right, let's get into some reactions. So for the first one that we're going to talk about is a reduction reaction of an alkene directly down to an alkane. And this is probably the most common reagent that you'll see in organic chemistry for reductions of double bonds or triple bonds. And so it has three different components. It has a source of hydrogen. And one thing to note is that a lot of times classes like to use deuterium here to kind of test your knowledge of the reaction. And so if you see D2, you should associate it with the same thing. It's just the deuterium instead of like the normal isotope of hydrogen. Next, we have a catalyst, which is this palladium on carbon. And essentially the way this reagent works is that there's kind of like a platform and there's a bunch of hydrogens that are sticking up from the hydrogen gas. And then the alkene comes on top of them and sits on top of them. And that's what allows for the reduction. Usually classes don't really ask for a mechanism for this. You just have to know the stereochemistry of the final products. All right, and then the last component here is going to be ethanol, which is the solvent. And one other thing I want to quickly say about the catalyst is that it can also be something like platinum on carbon or nickel. Those are the other ones that you might potentially see in addition to the palladium. All right, and so in this reaction, we get syn addition of the two hydrogens. And so we can see that in the two products that are formed here, in the first one, both of those hydrogens are dashed. In this other one, they're both wedged. And so you'll get a mixture, but it'll be syn addition of the two hydrogens. And then the other key reaction detail of this reaction is that you have no reaction with aromatics or carbonyls, except in certain conditions, which you'll get to in the upcoming chapters. But for this chapter, assume that the hydrogen only reduces those isolated alkenes and will not reduce benzene rings. So it won't reduce the ring that has the three bonds in the middle or a carbonyl, so where you have like the carbon double bonded to an oxygen. Neither of these functional groups will be touched in this reaction. All right, so let's do some practice problems here. So we have two reactions. In the first one, we have hydrogen that we're adding to this big reagent. And so we know that none of these groups on the right will be touched because they're all, they're not reactive enough for this reagent. And so the only functional group that is going to be touched is going to be that alkene on the left, and that's going to get converted to an alkane. So we're going to redraw the entire reagent and leave those other groups the same. And then we can just add in an alkane where the alkene used to be, and just make sure you conserve the number of carbons. We started off with 3 in that chain, and we ended up with 3. All right, for this next one, we have deuterium that we're adding. So we have to make sure that we draw in those deuteriums since they're not hydrogens. In skeletal representation, only hydrogens are implied. And so you have to draw in those deuteriums to make sure that you get this correct. And so we're going to keep the structure the exact same. That methyl group stays wedged. And so here we're going to add in two deuteriums. In the first reagent, we're going to have two wedged deuteriums and a dashed methyl group. And then we will draw the other product where everything stays the same, except now we have a dashed deuteriums and a wedged methyl group here on the bottom. And so those will be our two products of that reaction. Again, very straightforward reaction, easiest way to make an alkane out of an alkene. Basically, you're just taking the double bond, making it a single bond. If you have deuteriums, then you want to make sure you draw in both the dashed and the wedges. All right, so moving on, now we're going to talk about the hydroboration-oxidation reaction. And so this is a method that you can use to add on an H and an OH. And so since we're adding on a carbon-oxygen bond, this is going to be an oxidation reduction. And a key part of this reaction is that it follows anti-Markovnikov's, it forms the anti-Markovnikov's product. And for this, what that means is that the hydrogen is going to go to the more substituted carbon within the alkene, and the OH is going to go to the less substituted. And then another key part of this reaction is that we're going to have a syn addition to the reaction. And so this reaction has two different steps. In the first step, we have hydroboration of the alkene. And in the second step, we have the actual oxidation using peroxide and base. And so the product that we end up with here is going to have that OH goes to the less substituted right here. Hydrogen goes to the more substituted. And so we get the combination of these two products. And what we'll note is that the OH and H are syn to each other. So they're either both dashed or both wedged. And the OH is on that less substituted bottom carbon here. And so I'm not going to talk too much about the mechanism in this reaction. Each organic chemistry class has its own detail that it goes into. The one thing that I do want to kind of quickly bring up about this reaction mechanism is that the intermediate looks something like this, or that first step looks something like this. Where we kind of get this almost like concerted. Oops, I'm going to redraw that here. I have my double bond in the wrong place. Okay, so we have that the reagent kind of lines up like this. And this is a little bit simplified, so just make sure that your class, know the details that your class presents for this reaction. But we essentially get this from step one. Where we have that boron group is attached to that carbon on that bottom, and then that's the one that gets substituted for the OH. And so the reason this goes to, or has the selectivity that it does for the anti-Markovnikov's addition is because within the transition state, this carbon right here helps that methyl group is stabilized helps stabilize the partial positive charge that forms in that transition state. And so that is why you get that selectivity for that anti-Markovnikov's addition. Okay. And then when you do that oxidation step, the stereochemistry is retained. So that's why the BH2, when you get that OH on there, you get, it also stays dashed or wedged, depending on which one is started off with. All right, so one other comparison that I want to talk about is for the acid catalyzed hydration that we talked about a few chapters ago. So in this one, we know that we would also get a OH and an H added, but that the OH will go to the more substituted group here, or more substitute position. So we were following Markovnikov's product placement for this one. And so the key difference between these two oxidations, so for both of these, we're adding an H and an OH. However, for hydroboration oxidation, we get that the OH goes to the less substituted carbon. And for acid catalyzed hydration, we get that the OH goes to the more substituted position. And so the key difference is because of the intermediates that we have. So up here, I drew this intermediate here where we can see that that boron goes to that less substituted carbon, which can then get substituted by the OH. While in this mechanism, and I won't draw the whole mechanism again, but this reaction went through that carbocation intermediate where that positive charge went to that more substituted carbon where it's more stabilized. And so that's the key difference between these two and why we get different selectivities. As well as a reminder for acid catalyzed hydration, we get a mixture of products because that OH attacks a carbocation. And so we get both products where they're both wedged and dashed. All right, the next reaction that we're going to talk about is the use of mCPBA to make a epoxide. And so an epoxide has two bonds to an oxygen. And so we're increasing the number of carbon oxygen bonds. And so it's also classified as an oxidation reaction. And so the structure of mCPBA looks something like this, where we have a R group, and this ring that I'm drawing doesn't really matter. The important part of this reaction is this functional group on the right here. And so some classes will throw in a different reagent where it's a different R group right here. And what you have to recognize is that this circled part is capable of performing this reaction. And so for this mechanism, I'm just going to substitute this group on the left as an R group. And so I'll just write R for the mechanism here. And that's what I'll use to represent it within this reaction. And so for this, I'm going to redraw that alkene. And then I'm going to kind of orient this entire molecule in a certain way so that we can show all the arrows that are moving in this reaction. And there's kind of a lot of different pieces. So we can zoom in here. So for this one, the first part of this, or it's all one big mechanism, and so I'll kind of draw all the arrows at the same time. So we have that we're forming bonds with that oxygen. So both carbons or the electrons from the alkene are going to the oxygen, and then an electron pair from the oxygen is coming to the carbon-carbon bond. And so that's what makes those two carbon-oxygen bonds in the epoxide. We also have that those electrons from the oxygen-hydrogen bond go to the oxygen. And the reason that can happen is because those electrons from the carbon double bond into an oxygen can bind to that hydrogen. And then we also break this oxygen-oxygen bond here. And so we end up having electrons that go shift over to the left. And so altogether, this makes the epoxide. So we end up having this. And then we also form a carboxylic acid as a byproduct here. And so this mechanism is all one step. You just have to basically know those 5 arrows in that step. And this reaction will work with any reagent that has just a random R group, in addition to that highlighted blue moiety. Right. Okay, so the next set of reactions that I want to talk about are dihydroxylations. And so in a dihydroxylation, we end up adding 2 OH groups to an alkene to form something that's called a 1,2 diol. And so a 1,2 diol has two OH groups that are spaced one carbon apart. So you could think of it as like being 1,2 that the carbons are right next to each other. And so in this reaction, we have two potential products that we could form. We could have where the OHs are on the same. So this would be a syn addition, where those OHs are both wedged or both dashed. Or we could have where one is dashed and the other one is wedged, as in the case of this other one. And so we're going to talk about both methods of making these two different diols. And I intentionally kept no reagent here because we have to obviously use different reagents to create those two different combinations. And so if you're working with a practice problem where you have to create one of these diols, the first thing you should identify is whether they're syn or anti to each other. All right, so let's start off with the anti. And the reason I'm going with the anti first is because it uses that mCPBA reagent that we just talked about for epoxides. And essentially in that first step, we use that mCPBA to form that epoxide, and then we break it using base. And so I'll go through the mechanism of the steps for this one. And so I won't go through the mechanism of the epoxide again, but I'll just write C mechanism from above. It's the same thing that we just did, but the key part is that we're forming the epoxide. So I'll draw out the products that we get. And whenever we're adding an epoxide, keep in mind that we can get both the wedges or the dashes. They just both have to be, both of the bonds to oxygen have to be either both wedged or both dashed, but we can get that epoxide or mCPBA comes in from either side of that alkene. All right, in the next step, we're going to take the products that we drew from that first step, and now in that second step, we're bringing in base. So we have sodium hydroxide or an OH with a negative charge. And so those electrons can come in and attack. And if we recall from our epoxides unit, epoxides are opened up at the less substituted carbon in basic conditions. And that's because they're less sterically hindered at that position. And so they're more likely to have or be attacked there. And so when we draw these products, the stereochemistry of the oxygen is retained. And so we can see that for this first product, we started off with a wedged epoxide. So we're going to end up with a wedged O-. And then that OH that came in has to come in from the opposite side of the epoxide. And so it has to be dashed when it comes in. And so if we started off with the wedged one, like that first reagent, we end up with that dashed OH group because it has to come in from the opposite side, and the oxygen that swings open remains wedged. So we get that one from that first one, and then we get the other one from the second one. All right, so here we can see that we formed these new intermediates. And one thing that we have to be careful of is that this oxygen that I just highlighted in red, those are deprotonated because, or in this step, we haven't protonated yet. We just had that the oxygen from the epoxide swings open and forms that negative charge. And so our last step is going to be to protonate it using H2O. And similar to some of the other topics that we've talked about, make sure that you use H2O here. Since we're in basic conditions, we don't have H3O available to us, so we have to use H2O here since we're in basic conditions. All right, and so once we protonate, we can see that we formed those anti positioning of the two alcohols. And so those will be results in anti-addition. or anti-dihydroxylation. All right, so very useful reaction. It directly comes from our ability to form epoxides. And so if you see anti-OHs, then assume that you want to go through this mechanism. All right, so for this next one, this one's going to be the syn addition. And for this one, we want to use this other set of reagents, which is either potassium permanganate or this osmium-based reagent. Both of these have very similar mechanisms, but they end up with the syn addition of those OHs. And both of these will accomplish the same thing. And so for the purpose of your class, I would just recommend knowing or being able to recognize them as being capable of forming that syn dihydroxylation reaction. And then most classes don't go into the full mechanism of this reaction, but I'll briefly talk about how one of the complexes is formed so that you can see the reason why we get syn dihydroxylation. So let's do that potassium permanganate one. And so here I'm going to line up that potassium permanganate reagent. And so we get something like this. And so in this mechanism, similar to that mCPBA, we kind of get this simultaneous electrons coming from the oxygen manganate to the alkene, and then the other one's going to the oxygen. And so we get this set of reaction arrows here. And so then the intermediate that we get from that first step is where that manganate reagent kind of ended up sitting on top of that alkene. And we end up getting this. And then in the second step of the reaction, for what's under here, the base comes in and basically breaks up this part of the complex. And so we get, and it's like a multiple step reaction sequence. But we end up with getting those two OHs after that base or reaction with base here. But then those oxygens retain their stereochemistry, and so we end up having syn dihydroxylation. All right, I'll be posting some more practice questions related to oxidation reduction of alkenes. And so once you watch this video, I recommend shifting over and seeing those. And I'll see you in the next video.